Welcome to Math 2320, Section 4.6. In this section, we're looking at a technique called variation of parameters. It's more general than the method of undetermined coefficients, and it can solve many more problems. That doesn't mean it's easy, and it doesn't mean it's not messy. Method of undetermined coefficients works if our driving function is of a particular form. But if it's not of one of those particular forms, then the method fails. This technique will work, but it is a bit messy. Alright, so first off, we form the homogeneous equation. M squared plus 1 is 0, so m is plus or minus I. So my homogeneous solution is C1 cosine x plus C2 sine x. Now, in the method of variation of parameters, we make the assumption that our particular solution is of the form a function v1 and a function v2, which is multiplied by our homogeneous parts. So by putting that in, that gives me v1x cosine x plus v2 sine x. That's the particular form that it would take. We just need now to figure out what is v1 and v2. Well, plugging it into our problem and going into the theory, we see v1 prime times y1 plus v2 prime y2 is 0, and v1 prime y1 prime plus v2 prime y2 prime has to be our driving function. So this thing I've written on the right hand side is our driving function. So what we get when I fill in this information, here's our y1, y2. The derivative of cosine is minus sine. Derivative of sine is cosine. And so we now have two equations. Our unknowns are v1 prime and v2 prime. Now, we could solve this using elimination. It's fairly straightforward for two equations and two unknowns. The book uses Cramer's rule with matrices, so let's continue that. So if you look at the system, Cramer's rule says you form the determinant W, which consists of y1, y2, y1 prime, y2 prime. So when I do that, I get cosine squared minus a minus sine squared. So cosine squared plus sine squared, which is 1. To get my first solution, I need a top and a bottom. The top consists of placing the 0 and the cosecant in the first term, and then the second column remains the same. So 0 times cosine is 0, and then I've got a minus cosecant x times sine x. But cosecant is 1 over the sine, and so the signs cancel. I get 0 minus 1, which is minus 1. To get the top of my other answer, I put the right hand side in column 2, and column 1 is y1 and y1 prime. Alright, so what do I get? I get cosine x times cosecant minus 0. Well, let's see, cosecant is 1 over sine, so cosine over sine is cotangent. So far, so good. Alright, v1 prime is w1 over w. So that's minus 1. So if v1 prime is minus 1, then v1 is the integral of that, which is minus x. And we don't worry about the arbitrary constants. All right, so here's that. v2 prime is w2 over w, which is cotangent over 1, which is cotangent. And then if we integrate cotangent, well, how do you do that? That's cosine over sine. You can use substitution, let u be the sign on the bottom. And so when you integrate cotangent, you get ln absolute value of sine. So my particular solution is v1, which is minus x, times y1, which is a cosine. v2, which we just saw, was ln sine of x, and y2, which is sine of x. And so our full solution has our particular solution along with the homogeneous part. All right, and our second problem, we have y double prime plus y equals sine of x. We could solve this with undetermined coefficients. It would work because it's one of the forms that the technique does work for. So let's see, y double prime plus y equals 0. So I get m is plus or minus I. So for the homogeneous part, I get c1 cosine plus c2 sine. So my particular solution is v1 times the cosine and v2 times the sine. Setting up our two equations and two unknowns to solve again, it looks like the following. The derivative of the cosine is minus sine, derivative of sine is cosine. Here is our driving function. And again, you could solve this by doing elimination. I could multiply this equation by minus sine. I could multiply this equation by cosine, add them up, and eliminate one of the variables. But again, we proceed with the way to solve it with determinants. All right, so my original y1, y2, and their derivatives gives me cosine squared plus sine squared is 1. Placing the right-hand side in the first column, I get 0 times cosine, which is 0, minus sine squared. All right, W2, placing the right-hand side in the second column this time. Original column stays the same, so I get cosine times sine minus 0. All right, everything is very straightforward so far. And so, v2 prime is w2 over w, which is sine x cosine x. And v1 prime is minus the sine squared. To find v1 and v2, we simply need to integrate. Now that sounds simple enough. But there are a lot of tricks involved. First off, sine x cosine x. If you remember your trig and your double angles, we recall sine of 2x is 2 sine x cosine x. So dividing by 2, I get that the relationship for sine x cosine x is 1/2 the sine of 2x. Well, why do that? Well, that's because to integrate this is much easier than to integrate sine x cosine x. All right, so I'm integrating 1/2 sine 2x. So this is easy. We get a minus cosine for the antiderivative of sine. Because of substitution, I get another 1/2 out, so a minus 1/4 cosine of 2x. All right, and then I want to integrate minus sine squared. Well, again, I'm going to use some double angles. I know that cosine of 2x is 1 minus 2 sine squared of x. All right, so let's start getting this piece by itself. So bring the 2 sine squared to the left, it's positive. 1 minus the cosine of 2x, and then divide by 2. And so instead of integrating sine squared, I'm going to integrate 1/2 minus 1/2 cosine 2x. So that's pretty easy. Integral of 1/2 is minus 1/2 x. The minus here came from the minus in the front. So minus a minus makes that a plus. When I integrate, I get another 1/2 to come out, and I get 1/4 sine of 2x. So at this point, we've got v1 and v2. And we are essentially done. All right, so here's v1 and here's v2. And okay, v1 and v2. And so the problem is this. I mean, that's a fine answer. Nothing is wrong with that answer. But if you go all the way back up to where we started this problem and you look at the solution that WebAssign has, there is no double angles in the answers. Well, why not? Now, WebAssign would probably take this answer without any difficulties, but let's see if we can manipulate this answer into something we can see what happened. All right, so first off, I'm going to take my cosine x and distribute it in. So I get a minus 1/2 x cosine x. For this 1/4 sine 2x, I'm going to rewrite the sine of 2x as 2 sine x cosine x. Minus 1/4. Now I've got this cosine of 2x. I have a lot of possibilities, 3 possibilities for the cosine of 2x. I'm going to pick the one that I believe is going to make something cancel. And so I chose 2 cosine squared x minus 1. When you multiply in the sign, let's see what happens. Well, here's the first part. This 1/2 here, sine cosine squared is there. When I multiply this in, I get a minus 1/2 sine x cosine squared. So these pieces cancel and they go away. And I'm left with this 1/4 times this minus sign to give me a plus 1/4. All right, so now that gives me my particular solution. So here's yp. So we're closer to the answer that WebAssign has provided. So here's the homogeneous one. Here's our particular one after we've cleaned it up. Now the final step is to realize that this 1/4 sine x and this c2 sine x can really be combined. So because they're both sine x. So we're going to combine them together, but I'm still going to just label this as our arbitrary constant, and that gives us our general solution to this problem. A lot of work, a lot of double angle formulas. But in the end, we didn't lose any terms and things did work out.